What is the incident wave? What is the voltage here? Has someone figured it out? 3.75 volt. Any other solutions? Okay, so that's the instant wave, and then the wave hit this point, half of that is going to be reflected, because the reflection coefficient is 1/3, right? So it's going to be 1.875. Is that right? Okay, so that's going to be reflected, and then of course when this voltage hit this point, negative half of that is going to be reflected. So you have negative 0.9375. I don't know, I'm just trying to. Is this correct? Okay, all right. So, and so on. Okay, once this hit this, and then of course half of that is going to be reflected. Okay, so that's the reflection, all right? So once we know this reflection, what we're interested in is this voltage at that point, right? Okay, so how do we figure that out? What we need to do is, this is a 10 nanosecond point, this is a 20 nanosecond point, okay? That point is a 20 nanosecond location, right? So we'll just draw a straight line here, and then just add these voltages, okay? So basically, before 20 nanosecond, that voltage is 0. At 20 nanosecond, we have 3.75, okay? And then at 40 nanosecond, and this voltage is added to it. And then at, what is this point? 80? Oh, this is, okay, so this is 20, 40, and it must be 80 point, right? Yeah. So draw the timing diagram. You basically, as you can see, it's very easy once you have a bounce diagram. You basically just draw a vertical line here, and then just add the voltages correctly at the right time. Okay, so 20, 40, 60, 80. Okay, so before 20 is 0. At 20, there's a voltage here. That's 3.75, and then it keeps at that voltage until and 40. Then this voltage will be added together. That will give you 5.625, right? Is that right? Any question? If you see any errors, just point it out. You get a chocolate, right? Okay, and then it goes all the way to 80. At 80, then this negative voltage is going to be added to it. So basically, the voltage is going to drop. Okay. So are we in the ballpark? This is American line, right? Are we in the ballpark? Do you understand this question? No? Are we in the ballpark? Basically, that basically means are the values roughly correct? Okay, so the next value is this minus 0.937. Okay, so how do we get that one? It's 4 something, right? 4, 6, no, 473, roughly. Okay, basically you need to subtract this value from this value. You just subtract 1 first. Okay, that will give you this value. Then just add how much back? 625 back, right? Okay. So that's this value. Are we in the ballpark? How do we know? How do we know the value is roughly correct? Okay, let me add this back. This will give you 875. Is this correct? Is the trend correct? How do we know? It's getting closer to 5 volts. What's the final value of this circuit? About 4.5, right? Is it about 4.5? Yes. Okay. So of course, so 4.5 is somewhere on here. Okay. And if we do a little bit more calculation, we'll see whether this value is approaching 4.5, right? Right now it's not very clear. Okay. So it's probably going to do something like this. Okay. If we do a little more calculation. Let's see. Here's my solution. 5.625, 4.685. Okay. I don't have a simulation result here. Let me get a simulation result from SPICE. Wait, that's not a circuit. Okay. Okay, this is the correct circuit. Okay. So let's do a simulation. I can put the cursor on this so I can see the values. Okay. Okay, I can do a little bit longer simulation. So if I can simulate until, let's say 300. I can take a look at this value here. It's 4.497. So yeah. It's kind of funny, right? The waveform. So we calculate all the way here. Okay, right here, I believe. And you can see it goes up again and then approaches 4.5. Okay. And so that's basically, if we see that as we calculate this, if we see this going away from 4.5, for example, if it goes down here and then it's stayed here, then something is wrong. So that's what we mean by are we in the ballpark? Okay. So basically, the solution is roughly correct. Okay. It should be around 4.5 somehow. Okay. So that's the intuition. Okay. So we not only need to know how to use computer tools, we need to look at the problem and then decide what are the boundary values for this solution so that so we know roughly the solution is correct. Okay? That is, we know roughly where the ballpark is. Okay? All right, so this is the second problem. Yes. Oh, from the spice? Okay, yeah. It's probably because the source. Okay. Let me try to see whether I can, because the source, you notice the source is only 100 nanoseconds, right? The source period. But my simulation is 300 nanoseconds. Okay, so if I make this 300 nanoseconds, probably that will disappear. Okay, let me change all my period and then the pulse width to be 300 nanoseconds. And let me do a simulation again. I think that those should disappear. There. That looks better now, right? Okay. And you have to define the source to be longer than the simulation period. Okay. Otherwise, something funny will happen. So this is the waveform. Looks pretty strange, right? But that's what it is. Because transmission line, because of the ringing effects, it's pretty hard to just look at the circuit to find out why it is like that. Okay, but once you do a simulation, you can see it's pretty complicated, right? The step function will start as a step, but it's going to be bouncing back and forth until it's stabilized at 4.5 volts. Okay, this is a so-called transient. The reason we're starting this is because when you design digital circuit, sometimes you cannot afford to have this. This will add noise to your circuit. This may chip your circuit, okay, somehow, right? So it's more important for us to know all these signal distortions, because the class is about signal integrity. Signal integrity means no matter what the signal is, the function should be correct. Okay, the function should be correct. Of course, we cannot avoid having this ringing and then transient. They will always be in your circuit. Okay, but as long as it doesn't affect our functionality of our circuit, we're okay. Okay, any other questions? This one, I put it here, but we're not going to go through this. It's too much trouble, okay? And but I'm going to, basically, this is the example that we really, we're grateful that there's a SPICE software that can do this, Because if you do this manually, it's going to be very, very, very complicated. Okay, because first of all, we need to find out this source is a 10-volt source, so the incident wave is a 5-volt wave, right? Because this is 50 ohm, this is 50 ohm, so at this point you got 5-volt incident voltage, and it's getting pretty complicated. Okay, of course we can always draw some kind of ballpark description of the problem, and then we can fill in the values if we need to. Okay. So if we need to draw bounce diagrams, we need two bounce diagrams. Okay, because one is for this path here. Okay, so we need a bounce diagram. Let's start from this point. This is 1 nanosecond. That's 3 nanoseconds. So we're going to have this is 1, 2, 3, 4. So 1 nanosecond here, 4 nanosecond here. That will reach load 2. Okay, that load here, and then over here there's a boundary, right? Okay, so this is the first bounce diagram for these two lines. Okay, and so if you want to draw, okay, this is 1, 2, 3, 4, 5, 6, 7, 8. So this is 1 nanosecond in time. 2, 3, 4, 5, 6, 7, 8. So what should the bounce diagram look like? Okay, well, the wave is going to hit this point. That's the middle point, right? This is the middle. Now what's going to happen? What's the reflection coefficient at this point? This is 50 ohm. It's going to hit this branch here. There's a 50 ohm there, the 50 ohm here. So what does this wave see as a load? Say it again. 25 ohms. Because these two are in parallel. Okay. So this wave is going to see 25 ohms. So what is reflection coefficient? One-third, right? Positive or negative? Positive or negative? It's negative 1/3, right? So the reflection coefficient here in the middle is negative 1/3. So negative 1/3 of this voltage is going to be reflected. Okay, the rest will continue to go towards this first load there. Okay, then there's a reflection coefficient at a point. What is reflection coefficient here? What is reflection coefficient here? It's just 1/3, right? Okay, positive 1/3. So that positive 1/3, that reflection will go, and then it takes 3 nanoseconds to reach the middle, right? So it takes 3 nanoseconds to reach the middle, so it'll reach middle at 7 here. This is when it reaches the middle. When it reaches middle, what's going to happen? It's going to reflect, right? And then it's going to have forward wave. So that forward wave is going to reach the source at 8 nanoseconds. Okay? And once it reaches source, there's no reflection, because the source reflection coefficient is 0, because the source impedance is 50 ohms and transmission line is also 50 ohms. Okay? So once it reaches here, everything is fine. Okay? That's just this path. But there's another one, which is this one. Okay? So I have to deal with that one. The easiest way to deal with that one is just start with the middle and just draw 1, 2, 3, 4. 4 nanosecond. This is the second load. Okay? This is the bottom load. What is the reflection coefficient at this point? It's 1/5, right? It's positive 1/5. Okay. Now what's going to happen? What's going to happen here is, remember this is 1 nanosecond, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this wave is going to reach the middle, which is here, which is like this point. Remember these two are the same points. Okay. Then it's going to take 2, 3, 4, 5 nanoseconds to reach the second lobe. Okay. So this one and this one, these two are same. These two voltages are the same. Basically, the voltage, the wave that hit this point, it's because these two are in parallel, so the same voltage is going to travel on this line and then also on this line. Okay, because they're in parallel. So these two actually are the same voltages. Okay, and then of course once it reaches here, it's going to reflect back. It takes 4 nanoseconds to reach the middle point. Remember, this is the middle point. Okay. In the meanwhile, this voltage here is going to reach the middle point at 7 nanoseconds. Right? So at 7 nanoseconds, what's going to happen? There's a reflection here, there's the incoming voltage here. There's a voltage that's launched at this point. What is that voltage? Where is it? Okay, let's use V1, V2, V3, V4. Okay, so this is V1, right? This is V5. There's a voltage here that's going to launch into the bottom transmission line. Which voltage is it? V3. Are you sure it's V3? V3 is a reflection that reflects back to this line, right? And V4 is a forward-going voltage that's going to go into this line and this line at the same time, right? So it's V4. This V4 that's going to travel, and it's going to go down to that line. Okay, and of course, when this voltage reaches this point, some of this is going to be reflected. Let's say it's V6, and there's V7, and that V7 is going to, it's getting messy, very messy, right? That V7 is going to launch. That's V7. It's going to launch into both the first line and the second line. So it's getting very, very messy. So I use this example to show you why we need computer simulation. Okay, we need SPICE because we don't want to work out of this manually. Okay, because it's very, very messy.